So it's my pleasure to introduce today Martin Ward from Durham University. So Martin did his PhD at University of Sussex on X-ray galaxies, and then he moved to Cambridge for a 5-year postdoctoral contract before getting an assistant professor position at the University of Washington in Seattle. Then he got a lectureship at Oxford and a fellowship at St. Catherine College. And after 5 years at Oxford, he was the director of the X-ray astronomy group at the University of Leicester. And after 8 years at Leicester, he moved to Durham University, where he was the head of the physics department for 5 years. He's also a science team member of MIRI on board the JWST, and he's an expert in the area of supermassive black holes. And today he's going to talk about a super highly accreting active galaxy and a new multi-wavelength sample.
Thank you very much for that, and it's nice to sort of be virtually back in Cambridge. I would like to be there in person, and hopefully in the not too distant future it may happen. So I'm happy that we're now looking at my slides, because I think for a few seconds you probably saw a 3-meter large image of my face. Must look like some sort of dystopian Big Brother screen, but now you're just seeing my slides, which is much better. So to start with then, a few minutes, very few minutes, about a little bit of history and about myself, and then straight into the science. So this is a view almost from my house in Durham, and though you've been to Durham will recognise the cathedral and the castle. So I hope to welcome you to the shortlisted City of Culture, and we're all hoping for the best on that. We'll have to see how it turns out. So assuming I can now advance, yes. As I say, this is not about history, but just for a moment, the title of my chair, the Chevalier chair, by the way, it's not Chevalier. Those of you of a certain age will be familiar with a French chanteur called Maurice Chevalier. It's Chevalier, it rhymes with cavalier. He was the first professor of astronomy here for many, many years in the 19th century. He was also professor of maths and reader in Hebrew, and I'm only one out of the 3. His portrait is above me in the Great Hall of the castle. He's the chap with the long white beard, which I haven't yet developed. Looking at the observatory now on the right-hand side, this is our equivalent, although it's much smaller, of the observatory in Cambridge, which is a much grander affair. But it's a very nice building, and it has some famous assistants, which I won't read through, but one of them I might mention, and that is Carrington. So those of you that study the sun will be familiar with the Carrington event. Well, this is the Carrington. He did his studies of the sunspots here in Durham before moving on to greater things. And so that was nice to have a bit of history. I'm hoping in the future to turn this old building, which is currently unused, into the Sir Arnold Wharfendale Centre for Scientific Outreach, which I think would be a fitting memorial to him. And it would be nice to have something like this in the north of England. So I'm hoping that the RAS, of which I don't suppose anyone on the RAS is listening, but I'm hoping they may help us in this endeavour. So, of course, we now do modern research, such as the JWST, which I think we now call the Webb telescope. Although, of course, if you type Webb into Google, you will get a large number of hits, which have nothing to do with the telescope. We also have involvement with the extremely large telescope, the technology, and, of course, big simulations. Sorry, I misspelt that, apologies. That's supposed to be simulations by Carlos Frank and his collaborators. My principal collaborators in this project, Gary Furland and myself, you can see we have our priorities right here. This is us drinking together in Beijing. Chris Doan, who many of you will be familiar with. I believe she was in Cambridge just a day or so ago, but now she's back in Durham. She gets about. Chichen Jin, who is a rising star at the National Astronomical Observatory of China in Beijing. And Daniel Kainok, who is now a postdoc in Prague. Also Hermina Land and Jake Mitchell, who is my postdoc, my graduate student, I should say, in Durham. So this talk is very heavily reliant on these collaborators, in particular Chichen Jin, who is responsible for a paper in preparation, which is the body of my my detailed study of a particularly highly accreting active galaxy. Chris Doan, of course, you'll be familiar with, is very heavily involved in modelling. Other models are available, particularly to those folks in Cambridge. But in this particular case, I don't think it's too controversial, although we'll see when questions come in as to whether what I'm saying about this particular object is not entirely dependent on her models. So those of you that are in the active galaxy business will be familiar with the terminology, these plethora of acronyms: LINERs, luminous infrared galaxies, ultraluminous infrared galaxies, BL-LACs, radio galaxies, Seyfert's quasars, and so on and so on. And it's all very confusing and not very interesting, actually, because what we want to know is what's driving the actual activity and the diversity, and not these different names, which very often are related simply to how the things were discovered. But like with much of history, we're stuck with it. And so we do still use these names, although we're basically interested in the underlying physics. And so part of my talk today is going to be an attempt to slightly simplify, not in a major way, but at least in some small way, the AGN zoo, and to make some suggestions about some objects which appear to be different and certainly have different classification names, are actually the same basic underlying processes involved. So I know from chatting to your students, which was very entertaining and great fun, we talked about extraterrestrial life and extrasolar planets. Some of the audience there will not be AGN experts or doing it sort of day to day, so I'm going to spend a few minutes on some introduction. And those of you that are experts will have to just wait until we get to the nitty-gritty a bit later on. So active galactic nuclei have strong emission lines that cannot be explained by ionization from stars, even hot stars, even OB stars or Wolf-Rayet stars. They need ionizing photons of ionization potential, IP, of greater than a 90 eV and up to many hundreds of eV for the so-called coronal lines, which are seen in some of these AGN. The broadband continuum emission extends from the radio to the X-rays and even up to gamma rays in some cases, TeV regime, which is extremely high energies. And of course, this again cannot be explained by normal stellar processes. They are very variable on all time scales that we can measure, especially on short time scales. That's particularly interesting because it gives an idea of the size of the region, which we could never hope to resolve by spatial means. So the argument is that light travel time CT gives you an idea of the scale on which the emission can vary, because information has to be transmitted across that region. So it's very useful for studying the very compact regions of the AGN by using X-rays and even the optical. So recently, in the last 5 years, maybe a bit longer now, 10 years, there have been a new group of galaxies. They are AGNs called changing look AGN. And this is where they go from one particular observational state to another. So there's been discussion, as I said, with the acronyms for AGN. We're stuck with the history. They probably should be called changing state AGN, but because it's observational where they were first identified, we do call them changing look. But really we're talking about changing accretion state, or possibly obscuration, but mostly accretion state. Some AGN reach very high bolometric luminosities, up to 10 to the 48 and even beyond ergs per second. And these are, of course, the quasars. And the distinction between Seyfert galaxies and quasars is really only one of luminosity. And there's not particular interest or agreement on exactly where the transition between a Seyfert and a quasar occurs. It's really to do with what the observational and the modeling properties are that we're using. Very brief aside on variability, how far back can we go? Well, we can go back a long way. One of the most famous AGN Seyfert galaxies, called NGC 4151, we have a light curve, and light curve refers to anything that is varying. It can be X-rays even, it's still called a light curve. We have observations on photographic plates going back to around about 1900. I don't suppose Queen Victoria, had she been interested, would have known that NGC 4151 was in a very faint state at that time. But from these plates, which of course the accuracy isn't great, but if the variability is very, very substantial, then it's still useful information, was in a very, very faint state during that period of the Boer War. And various other periods of time when it was very bright and then not so bright. You can see that around the 1980s, technology improved and the errors were shrinking. This is because of the advent of electronic detectors, first photometers, and then imaging electronic detectors such as CCDs came along, and we have much, much better data. And if I was to zoom in, which I won't because this is just an aside, you would see how the expansion between round about the 1980s and now, the data is very, very good, and we can actually see how the trends are changing on timescales of weeks, months, and years. So the two basic types of CFOTs, AGN if you like, optical spectra, is how they were first observed, is that one group called CFOT1s have broad emission lines, and another group called CFOT2s have narrow, and you see here two canonical examples. The names aren't important. The very strong lines in the middle are from forbidden lines of oxygen, 5007, oxygen 3, and the broad line to the right is H alpha. H beta is just to the left of the oxygen lines, and there are other species as well. So initially it was thought that these must be very different types of object. But then came along the unified model, and I won't give the history of this. This picture, this cartoon, I'm sure some people may be groaning that I'm showing it because it's overused, but it's still really rather nice, and I still like to use it. The extra wording has been added from the initial Uri and Padavani paper, or Padavani and Uri, I forget which way round it was. And they suggested that geometry was very important. This followed on from previous advances by Antonucci and Miller, which I'll come on to. But they were stressing that the inclination is very important depending on what we actually observe in the optical spectra. So this sort of orangey thing is the so-called obscuring torus. This has changed much in our view of what it actually is over the decades from the time when this cartoon first appeared. It is now thought to be very clumpy and a distribution of clouds moving around. It's not like a simple donut. By the way, this cartoon, what you can see here is a cutaway middle bit so that we can see what's going on in the middle, because if that wasn't cut away, it would be obscured. So you can see the accretion disk is much smaller scale than the torus. And the radio galaxies are thought to be, when we view more down the emission where there's a jet, you can see on the top part of the cartoon, there is a radio jet illustrating radio galaxies, and the so-called blazars, which are very variable and have very weak lines. We are looking almost down the jet. So the angle between our viewing angle and the jet is very small. And you can see also marked the broad line region and the narrow line region, which are much larger scales. So the viewing angle is important. Polarized light was a key to our understanding. As you can see here, these spectra are of the same object, NGC 1068. The top view is taken in ordinary light, in other words, just a typical spectrum. It's only a part of the spectrum around about the oxygen lines and H beta, but underneath is the same object in polarized light. So what we're seeing here is the scattered emission of the hidden broad line region. So this was a great advance in our understanding of the unification of AGN. As I say, there have been many, many refinements to this since, but overall, this was the big advance to know that the CFOT2s with narrow lines were essentially the same as CFOT1s, but viewed by a different angle. A bit later on from that, it was clear that this could be extended to X-rays. Some AGN are very heavily obscured indeed. These are called the Compton thick examples, because they are so thick that even the soft X-rays, now this is an X-ray spectrum shown here as the X-axis in energy. The soft X-rays are absorbed by the photoelectric effect. There are two objects here, two separate objects shown, 3C273, which is a classic quasar, unobscured, and a classic Cepheid 2, Makarian 3. The previous object we looked at was 1068. This is another one which is well-studied example. And you can see here how dramatically it is that in the soft X-rays, the photoelectric absorption wipes out most of the emission, leaving only a remnant with a strong K-alpha line, which you can see here marked, that's iron K-alpha, whereas at very high energies, the X-rays penetrate through the very high column of gas, and you can see that the Makarian 3 spectrum shown in the green X's actually is very similar to 3C273. Although they have been scaled, they're not necessarily the same luminosity, but the key is the shape. So from 10 keV to 100 keV, a Cepheid 2 Makarian 3 looks just like a quasar. The other crucial thing about AGN is their spectral energy distributions. So from henceforth, I will just call them SEDs for short. And you can see here a rather complicated picture of the overall spectral energy distribution of a typical AGN made up of lots of different components. But really what I'm going to be talking about in the remaining time of this talk is the accretion disk and the soft X-rays and the coronal line, the coronal power law, shown here in blue and orange and red. The other things that you can see here are re-radiations from these particular components. In particular, the torus, shown here in the infrared from 1 to 100 microns, is essentially intercepted radiation from the inner regions, which is then re-radiated in the infrared. So how to make progress, having gone through the introduction? Well, obviously, as with all branches of astronomy and all other subjects of scientific endeavor, a blend of observation, models and theory. Large samples are very good for statistics, but not so good for many variables are involved. Just as a sort of analogy here, show a very large sample of cars. If you wanted to study the flow of cars or how cars worked, then you might study motorways or freeways, since this is Los Angeles, and you get a lot of interesting information from that, amongst other things, but you wouldn't necessarily understand how cars work. So detailed case studies are useful, but under the bonnet, taking the analogy with cars, it gets very complicated. And here's a poor equivalent of an astronomer trying to figure out what's going on under the bonnet. Is it driven by electric power, or is it petrol, or is it a hybrid? The translation of this analogy is, for example, is the outflow we observe in AGN a hydrodynamic outflow, or is it radiation driven? And we had an interesting conference here organized by Chris Doan on this very subject. And so if we want to take the inner workings to pieces, then it's better to study an individual object. If we want to have a broader view of statistical properties, then we look at big samples. Now, in the title of my talk, I said there were going to be two strands to my talk. One would be a big sample and one would be a detailed analysis or case study of a particular object, or a few objects, as it turns out. I'm going to gloss over the big sample, actually, this particular case, because it is in preparation by Daniel Kajnok, my former student now in Czech Republic. But just to tell you, it's like a sort of a trailer, if you like, an advert of what we're hoping to do with this big sample. There are many big samples, this is only one. But we liked this particular approach for various reasons, which I'll come on to. The sample was selected in X-rays based on the database of XMM Newton, optical spectra from the SDSS, and ultraviolet from the OM, the optical monitor of XMM Newton. Now, without going into too much detail, because as I say, it's very much ongoing, we have 800 AGN selected on the basis of a redshift less than 2.5, because we wanted certain emission lines to be in our observable region. More X-ray counts than 250, a somewhat arbitrary limit, but we wanted the signal to noise to be good enough to do some modeling in the X-rays. So this is in the EPIC instrument, one of the cameras on the XMM. And they must have optical monitor UV photometry, because we wanted to see what was going on in the UV region of the spectrum, because that's a clue to the accretion. They must have SDSS spectra, and there's no restriction for this on AGN classification, but they are largely unobscured because of the requirement to have UV photometry. So as I say here, a picture is said to be worth 1,000 words, but I think a spectrum is worth 1,000 pictures. In a sense, a spectrum is 1,000 pictures taken in very narrow wavelength bands. So as Gary Furland, who I hope is able to hear us way there from Kentucky, this is taken from his book with Don Osterbrock, the third version, shows the optical spectrum of an AGN, which you would never get in one go because it goes from the optical, by the way, this is rest wavelength we're looking at here in angstroms. So the very strong line to the right is H alpha, oxygen 3 H beta in the middle, and Lyman alpha at the ultraviolet. So you can see the wealth of information here from these various lines. We chose our wavelength coverage because we wanted to include at least one of the following lines, H alpha, H beta, and or magnesium 2. We wanted these lines because we wanted to get an estimate of the black hole masses. And you can see here the number of objects we have with each of these lines included. And it will be of interest when we come to finalize our paper to compare the black hole masses derived from these lines in the same object. There have been many studies where these lines have been used independently in samples, depending on their redshift. But we have a group of objects, I think it's around about 60, I'd have to check the exact number, where we have all three lines. And so we can compare the black hole mass estimates derived using these single epoch spectra for each of these lines independently. As I say, it's ongoing work. And I will go over this rather quickly because I want to get on to the case study. These are some preliminary results that we have where we're comparing the full width half maxima, which is one of the inputs into the black hole masses from single epoch spectra of the emission lines. Note the scatter when we compare these full width half maxima for different lines. This demonstrates that some lines are better than others for black hole mass estimates because the scatter is less. We note here that we can derive also as a byproduct the ratio of broad H alpha to broad H beta, and we find that to be 3.9, which is not quite case B, but that's consistent with other studies. And that really is a symptom, or a result, I should say, of the fact that we've required that we have UV photometry from the OM optical monitor on XMM Newton, and hence most of our objects are unobscured. Conscious that time's moving on, so I think I will skip over this. This is just the preliminary results showing that we do get different mass estimates using the different lines, and we also get different mass of the black hole estimates when we use the full width half maxima line profiles and when we use the continua as part of the black hole determination, as has been demonstrated in the past at 5100 and 3000. And we're looking into why there are differences and what is the cause of these differences. We're also following the work of Bertoluccio and Rizzatelli from 2016 to calculate the 2 keV luminosity and the soft X-ray spectral indices. And again, this is consistent with previous studies showing an average value in the soft X-rays for the photon index around about 2 with a broad range. We're also going to look at the correlations between alpha OX and the UV and X-ray luminosities. There are some subtle differences with previous work, and we're investigating these in terms of the black hole, sorry, that should be black hole mass and the Eddington ratio, because we believe that part of the scatter here can be reduced if we include these other parameters, the black hole mass and Eddington ratio, in the analysis. Radio objects, we have about 10% of our sample are radio loud, and we're looking for differences between the radio loud and radio quiet in terms of other properties. We can see there definitely is a difference in terms of the full width half maxima of the H beta or the magnesium 2 line, and whether they are radio loud or radio quiet. And we're seeing if we can take into account whether they're compact or extended radio sources by using the fact that we have a slightly higher spatial resolution measurement at the same frequency and a lower resolution measurement, and those which are higher above the correlation curve here for the lower spatial resolution are probably the extended sources. And so we can separate the classes, at least in some sense. We can separate the two extended from the compact classes. So now back to the detailed case studies. It's very important news, which isn't news to AGN studies, but possibly to people that don't do AGN as their principal research study. AGN have both inflows, which of course we've known for ages, accretion onto black holes, and outflows. Well, we've known about radio outflows in terms of double radio sources, Cygnus A, beautiful lobe radio sources for a long, long time. But when I say outflows, I mean more than just radio jets. I mean winds. And the last 2 decades or so, outflows in terms of winds have become increasingly important. So I want to introduce an important parameter called the Eddington ratio. And this goes alongside the black hole mass and the accretion rate as a key parameter. So the Eddington limit, and related to it, the Eddington ratio, is radiation when the radiation pressure is equivalent to the gravitational pull. And so this is undergraduate stuff. I'm sure many of the students will have had this in their lectures, their first year lectures on astronomy. And so I won't go through the derivation at all, but it's a simple derivation of the radiation pressure equal to the gravitational pull. And you can see the Eddington luminosity is defined then as this relation shown here in the green box. One interesting thing, which I think I'll point out for the benefit of maybe just a few people in the audience, is the interesting reason why the sigma, which is the Thomson cross-section, is the electron Thomson cross-section, whereas little m is the proton mass, big M is the black hole mass. So why are we linking the electron Thomson cross-section with the proton mass and not the electron mass? Well, of course, as those of you that do this will know, it's because the electron Thomson cross-section is much larger than that for the proton, and hence it's a larger surface area for radiation pressure, whereas the actual mass involved is the proton mass, which is 1,836 times bigger than the electron. So that's why these two proton and electron parameters appear differently in the relation. In other words, the electron mass is not relevant and the proton cross-section is not relevant. So I'm going to consider a subclass of AGN called narrow-line Cepheid-1s in the remaining time in my talk. So as the name suggests, these are like Cepheid-1s, but they have narrow lines. And to be very clear, because of the unfortunate historical terminology which we're stuck with, narrow line does not mean Cepheid-2s. Cepheid-2s do have narrow lines, but we're referring to narrow forbidden lines and narrow permitted lines if they're obscured by the torus. Whereas the narrow lines here for the Cepheid-1s are referring to the H alpha, H beta, and other lines, magnesium 2, etc. So they are narrow, broad lines. Sorry about having to put it that way, but that's what it means. The full width half maximum of the normally broad lines is much less than for a typical Cepheid-1, having cleared that up. So these objects have often high Eddington ratios. Some of them can be super Eddington. In other words, they can be higher than the Eddington ratio. So one might naively say, but that's not possible. We've just shown that there's a balance between the pull of gravity and the push of radiation pressure. But that's only in the simplistic accretion where everything is spherically symmetric. We know that's not true. It's much more complicated. So in the much more complicated regime which we have in these objects, you can have super Eddington examples where, at least for a period of time under certain conditions of the accretion disk properties, one can have super Eddington ratios. So what are the observational properties of narrow line Cepheid-1s? And finally, do they look like other objects called weak line quasars, weak emission line quasars? So here are some general properties. They were initially characterized back in the 1980s by Goodrich, a student of Don Osterbrock, to have the following properties: full width half maximum of H beta less than 2,000 kilometers per second, whereas a typical Seafort-1 would have perhaps 5,000, maybe even 10,000 kilometers per second, and a flux ratio, or even a luminosity ratio, because the lines are close together, it's the same thing, of oxygen 3 forbidden to H beta of less than 3, whereas in a typical Seafort galaxy, this would be a much higher ratio. The other interesting fact was that the Fe2 lines, permitted ion lines, which occur many places, but either side of H beta, shown here in the spectrum below, called eigenvector 1 by Borinson, are very strong. And this is shown to be a characteristic of these objects, and it must be telling us something about what the broad lines are seeing in terms of their ionization state and the accretion processes. In addition, and this was after the initial characterization of narrow-line Seafort-1s, it was found that the black hole masses were rather low in comparison with the typical Seafort. There's a big range. It goes from 10 to the 5, in some cases even slightly less, to 10 to the 7 or slightly more. But this is lower than the average values for a typical Seafort-1. They also have a high mass accretion rate, close to the Eddington ratio. So below here we see a typical spectrum, and underneath you can see the Fe2 spectrum taken away to reveal the underlying continuum, shown here in the green dashed line, which is of course of interest if we're wanting to study the accretion disk and whatever else might be contributing, possibly even some host galaxy emission at the redder wavelengths, but mostly the accretion disk at the shorter wavelengths to the underlying continuum. Where does the population fit in? Well, this is slightly complicated, but I'll spend a few minutes explaining this plot. So it shows the regions populated by various types of active galaxy. Principal types being radio quiet, AGN, the QSOs, radio loud, broad absorption line QSOs, as the name implies. They're similar to the others, but they have very strong absorption lines, and the narrow line Seafort-1s. So the X and the Y axis are simply explained by the Eddington ratio, shown here increasing from right to left, going up, and the mass accretion rate going down, m dot. Now the black hole mass in this particular plot is shown as a diagonal component or property. So you can see here that the narrow line Seafort-1s are here in the top left region, and so they have, as you can see from reading off the axis, a high Eddington ratio and a high m dot compared with the other objects. They also have steep spectra in the soft X-rays. Gamma is the spectral index. A strong soft excess shown many years ago based on ROSAT data, and of course confirmed and much better studied when we had experiments such as ASCA and the more recent generation of X-ray satellites, XMM, Chandra, and so on. They have strong X-ray variability, but weak optical UV variability. You can see here a particular object called NGC 4051. This is the percentage of variability at different wavelengths and in two principal lines, H alpha and H beta. Now the lines, of course, are responding to the continuum variability. This is the basis of reverberation mapping. So their variability could be considered to be somewhat different from the continuum variability, as they're responding from the effects of the continuum variability. But you can see how the X-ray variability as a percentage over some period of time is very, very high, nearly 50%, whereas as we go to longer wavelengths, it becomes much less. And you can see from the left-hand plot a light curve shown here with Julian date in days and the X-rays of a particular narrow line Seafort-1. So their SED properties are different also. For a group, and this was work done by myself, Chris Doan, and my student, Jin, some years ago now, we showed that their SEDs are very different as well. We grouped them into low, medium, and high. Of course, there's a continuum of objects, but we wanted to see what we could say about trends within groups. The low Eddington ratio, you can see, have much less of a bump in the optical UV and much stronger X-rays, these are the blue, whereas the mid-Eddington, shown here in green, are sort of halfway between, and the narrow-line C-1s have much stronger optical UV, soft X-rays, but much weaker hard X-rays, and also a different slope. But it's not that simple. Not all narrow-line C-1s have simple steep X-ray spectra. Many of them, depending on the viewing angle, can have warm absorption, partial covering factors, reflection, and so on. And you can see here the wobbly spectrum on the right-hand side is an example of what happens when you have changing covering factor, where you have a warm absorber which is changing its properties, its partial covering factor with time. So there's one level of complexity, whereas the other object shown here in red is much more stable because it's viewed more directly and is not modified by being viewed through this absorbing column of gas. Not all of these objects have high mass accretion rates. The narrow-line C-1s, you can see here there's an example of one with a very low mass, but also a very low Eddington ratio. The two examples, in fact, shown here as NGC objects. Black hole spin is also important because that changes the efficiency of accretion. Much work has been done on this by your famous astrophysicist in Cambridge, by us and by more recent people as well. Radio loudness has been studied also in detail, and this has an effect because the jet can contribute to the hard X-rays. And finally, another complexity is quasi-periodic oscillations, called QPOs, are seen predominantly in narrow-line C-1s. They are to do with the inner accretion disk and instabilities. We don't know exactly how they work, but they do appear to be characteristic of narrow-line C-1s, the best examples being in that class of object. So how super Eddington can these objects be? What's their upper limit? And I think testing the extremes can often tell us something about the processes. So I've already mentioned the Eddington luminosity, the Eddington limit. So this is just a repeat of the formula you saw before, turned into parameter space so that you can plug in a black hole mass shown here in solar luminosities to give you an actual value. And then the Eddington mass accretion rate shown here, m dot, is related then to the radiative efficiency, which is mu0. For a spin of a standard accretion disk, it's about 0.06. That's a SUNY-IF disk, a standard accretion disk. So the Eddington ratio, often written as lambda Eddington, is defined simply as the volumetric luminosity over the Eddington limit, shown in the above equation. And this then can be expressed in terms of the radiation efficiency, radiative efficiency, and m little dot, where m little dot is the mass accretion rate in the outer accretion disk. So we can get L bol by integrating the broadband SED, spectrum distribution. But of course we need a lot of observations for this. We need a lot of detailed information. Whereas m lambda then, lambda Eddington can be measured directly if we have that information. So obviously the Eddington mass shown here, m Eddington, over the m dot can be measured, the accretion rate, if you know the flux in the outer disk where the UV and the optical emission is produced. So little m dot is related by the formula shown here. There is an inclination effect, which is cos to the 3/2 inclination angle. And of course, this will have to be an average with the black hole mass appearing as m squared. So L optical UV is observed in the UV. So we can measure the radiative efficiency by relating the Eddington ratio, L ed, over little m dot times the standard accretion efficiency, lambda mu0. So if we consider an extreme case of a super Eddington object, shown here, I'm afraid the names are rather long and not very important. There's just one particular name I'll come to in the last 5 minutes or so of my talk in a few minutes. And that's the one which we think provides, if you like, a missing link with the weak line QSOs. So you see here a very nice SED where we've assembled lots of data. The data are not necessarily simultaneous, but that doesn't matter too much, providing the accretion disk and the soft X-ray data, the optical and the UV, is quasi-simultaneous or simultaneous with XMM, because you can get the X-rays and the UV simultaneous. The infrared doesn't matter too much if it's not simultaneous. So you can see this object does have a relatively low mass, a high Eddington ratio, 4.6, a high little m dot, and a relatively lower radiative efficiency, about 40% of the standard disk radiative efficiency. So what we think is happening here is that because of the high accretion rate, we think that the inner disk is puffed up. You can see here the model of the disk below the SED, and the standard disk is shown here in reddy orangey color, but it gets puffed up because of the high Eddington ratio. And this then modifies the properties of the accretion flow, the radiative efficiency, and also modifies the properties of the outer regions of the accretion disk, because they see a different spectrum than they would see if the disk was not puffed up, and then indeed the torus as well. So here's the extreme object again. Now, we don't have information in between the shaded region here, connected by the blue line, because sadly, galactic absorption means we don't have data in that region. It's absorbed by gas in our own galaxy. So we have to rely on models. And of course, the models can be modified depending on how we think we link the UV optical up with the X-rays, the soft X-rays. So there are different estimates. There are also, they're shown here as L1, L2, and L3. That's one uncertainty. The other uncertainty then would be the uncertainty in the black hole mass, determined by these methods shown here. So there are a range of uncertainties here, which we have to be aware of. And this then will give different values depending on what we choose to use for these values, depending on the black hole mass and depending on the L1, L2, L3, which we choose to fit by the models. So here is a very extreme narrow line CFOT1, which I'm going to use now as the example of a link with the weak line quasars. So again, we have very, very nice wavelength spectra, multi-wavelength spectra, SEDs, shown here. And you can see in this case, it is the most extreme example, not in terms of its mass, but in terms of its Eddington ratio, L-bol to L-ed, in terms of its little m dot, and in terms of its low radiative efficiency. As you can see, it's only 20%. I'm running out of time, but I think I'm just about going to make it in time. General properties of super Eddington objects. So their optical spectra, there's a range of these here shown in this, this composite diagram. They all look quite similar. These are all different objects, but their optical spectra look rather similar. Slight differences as you go to the red end, possibly due to contamination from host galaxy. But when we come to the other properties, such as the relationship between the broad line region and the luminosity at 5100, we see that the narrow line CFOT1s follow a different track. And that is because the relationship between the broad line region radius and the luminosity depends on what the broad line region is seeing in terms of the X-ray, in terms of the 5100 luminosity. And if this is shielded because of a puffed up disk, then the relationship will break down, as is shown here on the right-hand side, where the red points are actually not in the same region as the black points, which are for the normal CFOT galaxies, because of shielding due to the puffed up disk. So their change of properties causes this difference in relation shown here. The X-ray spectra of super Eddington objects, the soft excess, typically a low temperature, optically thick continentalization. They have a very extended corona, and they have a weak reflection component. and the inner disk component has a very strong soft excess. I won't go through all the examples. These are just references to examples. So the propagation of X-rays through the intervening material and reflection back can give rise to lags. So recently, well, a few years back now, we studied these lags caused by the fact that the disk is puffed up in the inner regions. And you can see here that we established that the soft X-rays in this particular object lead the hard X-rays due to the reflection from the puffed up disk. Again, in the same object here, we showed, sorry, this is a different object. We showed that the ion reflection, this is a different object, 0134. We showed that the ion reflection lags by quite a long time, 10 kiloseconds, due to reprocessing from the puffed up disk, as shown here in the arrows. So I need to move on quickly because I think I'm already slightly over time. The complex X-ray spectra of narrow-line Cepheid-1s is largely due to the viewing angle. So the ones that appear to be very simple, shown here in the red and the blue, are because we're viewing them straight down, shown here in the cartoon, whereas the complex objects are shown because we're viewing them at an angle, shown here through the dots, which are supposed to be absorbing gas. And that can modify the spectrum dramatically. That's showing the typical spectra and how they are different from normal Cepheids because they're high Eddington ratios. I'll skip over that because we're running out of time. To distinguish between two accretion flows, a slim disk flow and a disk plus an outflow, M dot is much better because it gives a true accretion rate through the outer disk, and it's also easy to measure. So that's a good number to measure. And you can see here, I'm coming to the last couple of slides, RxJ0134 has a very, very high M dot in the outer disk and a very low radiative accretion efficiency. So this is the picture that we have, simple narrow-line Cepheid-1s viewed from above without intervening puffed up disk and clumpy disks through which the broadline region is viewed. So could some narrow-line Cepheid-1s be the equivalent of weak-line quasars? Well, here we have examples of weak line quasars. They have low equivalent width, which is the different definition of a weak line. We're looking in the UV now because quasars are high redshift. So these are the typical SEDs of weak line quasars. Their properties are similar to normal quasars, but they have depressed X-rays with respect to normal quasars and also lower torus, in other words, infrared emission, because they are viewed through this puffed up disk. And we have comparisons here for a typical weak line quasar, PHL 1811, and various narrow line Cepheid-1s. So moving to the crux then, the last conclusionary slides here, optical spectra of our narrow line Cepheid-1s look very similar, depending on which one you look at. You can see in comparison with the weak line QSO, then they're all pretty much similar. However, when we look in the UV, there's a big difference. Most of the narrow line Cepheid-1s look very different. They're not like the weak line quasars, but one, RxJ0145-42, a boring name, I'm sorry, but that's what it is very similar. Why? Well, we believe it's very similar. This is just hammering home the point that it's very similar, because we think that it has a different accretion flow because of its very, very high little m dot. And you can see here from the green spectrum, which is the PHL 1811, the weak line QSO, and the black line, which is the extremely high Eddington ratio object, is much closer to the weak line QSO than are the other narrow line Cepheid-1s. So the torus emission is depressed in this object because the accretion flow is modified due to a very puffed up disk. And so this is second to last slide, I think. This is in our paper in preparation by Jin. The difference being that normal narrow line Cepheid-1s, if I can call them that, have a slightly puffed up disk, but by no means as thick and in a different region. It's closer in, whereas the extreme case of 0134 has a very puffed up disk and reflection and also a much more modified view of the broad line region, just as is the case for weak line QSOs. And this shows then the idea that that is the reason why this one extremely highly super Eddington narrowline Seafort-1 is the most similar. So it's a continuum of objects. So, summary then, the object in question is not like the narrowline Seafort-1s that I mentioned, because it doesn't have the strong soft X-rays, similar to the weak line QSOs, doesn't have a strong soft X-rays. It's highly variable, and it has weak lines in the UV. So in answer to the question that I asked at the beginning, M dot, that's through the outer accretion disk, can be very high, from 100 up to 100. The bolometric luminosity over the Eddington ratio, the Eddington limit, can be very high, up to 10. Radiation efficiency decreases as M dot increases because of the advection in the wind, and possibly extremely radiative inefficient and very high M dot narrowline Seafort-1s are indeed like the weak line QSOs. So we've gone in some small way to reducing the AGN zoo, and in some sense unifying in at least some properties, the properties of these AGNs. I'm sorry I went over time, but there we are. That's it.
Let's try.
I can't hear you at the moment.
Wait. Can you hear me now?
Yes, I can, yes.
Okay, cool. So let's see if there is any question in the room or on Zoom. I can't see any question. Do you have any question on Zoom? If you have a question on Zoom, just type your name, or maybe you can just unmute yourself. Okay, so maybe I can ask. Oh yeah, Mark, can you unmute yourself?
Oh yeah, it was. Can you hear me? Okay.
Yeah, fine. Yeah.
Yeah, it's very interesting. So my question has to do with estimates of MDOT. The inner part of the accretion flow you're modeling, given a certain MDOT measured from further out. Yeah. If there's any wind presence driving material off the disk in between those two states, then I would worry that the estimate of MDOT for the inner disk might be biased. Is that something is that a bias you can rule out, or might?
I think it's a good question. Well, let me sort of pose you a question. So the fact that the outer disk really does fit very, very accurately, the slim disk, would that, if your scenario were true, would that modify, or would it just scale? Because it does fit extremely well to the disk models.
Yeah, that's a good reflected question. I think so. I mostly deal with magnetically driven winds, and then I think it would depend on the radial magnetic distribution. I can imagine that if an AGN goes into a super Eddington phase, then a lot of the magnetic field would be drawn in. Now, maybe it would be drawn in so far that it wouldn't be an issue, but if it's drawn in, then I could still see a good fit happening further out. But then maybe
I think that's absolutely right. And the Chris Stone conference, not sure whether you were there, but there was
I wish I had been, but
a huge amount of discussion on the role of magnetic fields. And as only an observer, my impression was that this is restricted very much to the inner regions within the puffed up region. But maybe I can be contradicted, but I think that's where most of the pundits assumed that the magnetic effects were dominant.
Yeah. I worry that some of that may be that some of the puffing is assumed to happen with the magnetic field, and then those are coincident. But
if the puffing is also influenced by magnetic fields, then we have to modify things. Yes.
Right. Yeah. Thank you.
Do we have any more questions? Nothing in the room. Let's wait 1 minute. Okay, then if there is no more question, I think. Oh yeah, there is one. Sorry, Richard.
Martin, do you have any handle on the sort of the time scale for how long objects can be super Eddington?
Yes, I think we do. That's something probably that I'd have to go back to some papers to look at, but particularly when things, well, the ones that are super Eddington, which are complex, of course. Or do you mean, I mean, they can change their numbers, but then that's just a viewing effect, isn't it? That's when they have sort of column density and they change a lot, then you mean actually the accretion itself. Then I suppose not. I mean, it's probably linked in some way, which I assume people are studying, with changing look AGN. So what I'm not sure of, and it would be a rather interesting thing to investigate, is whether any narrow line C-foot-1s have done their changing look. As I'm sure the pundits in the audience know, the AGN people know, there's now a growing body of AGN which have gone from C-foot-1s to C-foot-2s, C-foot-2s to C-foot-1s, their so-called changing look. But whether there has been a good example of a narrow line C-foot-1, which of course then would tell you how much the time scale is for changing, if we could catch one on the go. So if anybody knows, please let me know. I think that would be something good to look into.
Let's change the question. Okay, so I think we can stop there, and thanks Martin again. Thanks a lot Martin for your very nice talk.
Yeah, sorry I used up the question time. It's the problem of not having given a talk in a year and a half. Anyway, thank you very much for the invitation, and hope to see you in Durham at some stage.